Pleasant day to everyone. Today we are going to discuss part 2, Module 5 for the subject CE 3151, Lecture and Laboratory, Numerical Methods for Civil Engineering Problems. So in this lecture, we're going to discuss the bracketing methods for finding the roots of nonlinear equations, specifically the bisection method. So for the bracketing method, this is a method in which the assumed values of the knowns will always converge to the true solution of an equation. We start off with two initial guesses, just like for incremental search method. We have XL and XU, or the lower and upper limits of our bracket, which are required now for the root of the equation. So if one root of a real and continuous function, f of x, is equal to 0, then it will be bounded by the values xl and xu. And the root now will give us or follow the condition that the f of xl times the f of xu, or function of xl times the function of xu, should be equivalent to 0. And for bracketing method, there are two types under it. The first one is what we call the bisection method and the false position method. So we start off first with the bisection method, which is the simplest bracketing method that we use to determine the roots of nonlinear equations. So this is also called as binary chopping, interval halving, or the Bolzano's method. So in this method, this is a type of incremental search method in which the interval will always be divided in half. The interval at which the function changes sign is where our root is located. The interval is divided in half, with which the root lies in the midpoint of the subinterval. So this process is repeated to obtain refined estimates. Okay? So the steps in bisection method will as follow. So the first one, same as for incremental search method, is we choose our initial limits for our iterations, XL and XU. And with our initial assumptions, we compute further functions, and the product of the functions should be less than equal to, or less than to 0, in which the function of x now changes signs between XL and XU. So if there's a change in sign, meaning the root will be lying down on the values of x in which the change occurred. And then step 2, we now estimate the root xr for the equation fx equal to 0, in which this is now, or xr, is the value between midway or midpoint between xl and xu. So we use the equation xr is equal to xl plus xu over 2. Okay? So this is our xr. So for step 3, we check now the product of the function of xl and the function of xr, their products. If it gives us a value less than 0, then it means the root is between xl and xr. If the product now is greater than 0, then our new limits or boundary will be between xr and xu. And if the product of xl, the function of xl and the function of xr is equal to 0, it means that xr is our root of the equation. So upon checking for the limits or the new limits of our equation, the new estimate now will be applying the new estimate using xr equal to xl plus xu over 2. And we compute now for the approximate error by using this equation. So we have epsilon sub a, or the absolute error, is equal to the xr new minus xr old all over xr new times 100%. Then for step 5, we check the absolute relative approximate error. If it is less than the pre-specified tolerance, epsilon sub t, or if the maximum number of iterations is reached, then we have to stop. Or if the function of, or the product of the functions of xl and xr is equal to 0, then we also stop with our iterations. If this is not the case, then we have to repeat our procedures using the new upper and lower guesses that we have taken from step 3 and repeat again with step number 2. So the advantages of bisection method is that it always converge on the true value of XR, and that the root brackets would always get half with every iteration. The disadvantage would be that there is slow convergence between the roots of the equation, and if one of the initial guesses is close to the root, then the convergence will become slower. So drawbacks of bisection method is that for function of f of x, when it just to understand bisection method under the bracketing method, we have an example. So we determine the root of the given equation. Function of x is equal to negative 0.6x squared plus 2.4x plus 5.5. So in this problem, we are to employ an initial guess of xl equal to 5 and xu equal to 10. And we are to compute likewise the approximate percent relative error epsilon t. So for our solution, so we have our lower limit, so substituting our limit in our equation, so we get 2.5. Then we have our upper limit, 10, and substituting the value of 10 in the equation, we get the function of xu is equal to negative 30.5. So next step is to compute now for the average or the midpoint of our lower and upper limit. It's 5 plus 10 divided by 2 will give us x sub r, or the approximate r, x is equal to 7.5. We now compute for the function of x sub r. Substitute 7.5 in this equation, will now arrive at negative 10.5. Okay, so next is we now compute for the error, which is 7.5 xr minus xl divided by 7.5 times 100, which will give us a value of 33.33%. So in this case, we have a very large error. So we try to move again to the next iteration. So we'll use the lower limit, and our upper limit will be a new value which is equal to our x sub r. So for our next iteration, lower limit is 5, x sub r, or the upper limit is 7.5. So we have computed already our value of functions. So compute for the new x sub r, 5 plus 7.5 divided by 6.25 we get E function, substituting 6.25 in our equation. So we get value of negative 2.9375. Okay, so next, we solve for our error, which is now XR minus XL all over XR will give us 20%. We still have a higher or very high relative error, so we continue with our next iterations. So using our new limits, lower is 5, upper is 6.25. Okay. So with our new lower and upper limits, compute for your x sub r. So that's 5 plus 6.25 divided by 2, we get 5.625. Substitute the value of x sub r in our equation, we get a value of positive 0.015625. Computing for the relative error, we now get a value of 11.11%. So again, it's a high percentage error, so we continue with our iterations. There is now a change in the sign conventions. So we have a new set of lower and upper limit. So we'll have the limits at 6.25, our upper limit, and the lower limit now is 5.625. So take note, shortcut, if we have a negative value for your fx sub r, then we have our limits as xl and x sub r. If our function of x sub r is now a positive value, then the limits will be x sub r will become your new xl for the lower limit, and we retain your x sub u or the upper limit. Okay? So we have our new set of lower limit and upper limits from the previous slide. So again, we solve for the new x sub r, it's 5.9375. The function of x sub r now is negative 1.402. Computing for our error, we get a value of 5.26%. So it's still a big error. And then we have fx sub r is negative. So we get a new set of lower limits and upper limit for our next iteration. For our new x sub r, that will now give us a value of 5.781. Computing for the function of x is equal to negative 0.6776. Computing for our relative error will give us a value of 2.698. So if we are given a value of e sub e, let's say 3%, then we could stop already at this iteration. But since we are not given any value of conditional error, so we continue again with our iteration. So in this case, fx of r is again negative. So we have a new set of the lower and upper limits with xl 5.625, xr is 5.781. So with this new limits, solve for xr again, we have 5.703. Function of x is equal to negative 0.327. Computing now for e, we have 1.368%. So f sub x or f of x is negative for x sub r, so we'll still use lower limit 5.625 and a new upper limit of 5.703. So from our previous slide, we have our xl and xu solving for x sub r. We get 5.664 with a function of x equal to negative 0.155. And computing for our error, we get a value of 0.89%. So if we're going to check based on our rule, instead of the sign convention, our rule is the function of xl times the function of xr. xl is positive and xr is negative, so it's a negative value, so less than 0. So therefore, our new limit will be xl still, and our xr will be our new x sub u. Okay, so we have our new limits xl, xu, solving for their x sub r, we get 5.664, limit is negative 0.554, error is equal to 0.689. So if you can see, we have the same value of xr, same value of error. Even if we continue with our iterations, we'll still be using the same lower limit and same upper limit. So with that, we stop at this iteration. So therefore, our estimated value of the root of x is equal to 5.664. And take note that for this value, this is only one value of x. Okay, so let's have another example, number 2. Determine the drag coefficient c needed to reach a velocity of 40 meters per second if m, or the mass, is equal to 68.1 kilograms, time is equal to 10 seconds, and the gravitational acceleration is equal to 9.8 meters per second squared. We have the equation for the drag coefficient equal to mg divided by c times 1 minus e raised to negative c over m times t minus v. So we could simplify this equation using now our constant values. The function of the drag coefficient c can be simplified as 667.38 over c times the quantity 1 minus e raised to negative 0.146843c minus 40. So this will now be our working equation for finding the roots of c. So using this equation, first iteration, we assume your xl and xu. Let's start off with 12 and 16. So from there, we solve for our functions of x. So for xl, that's 6.067. xu is at negative 2.269. And then, second step is to solve for our approximate root by adding xl and xu divided by 2. So we get 14 as our xr. So with that, we compute for the function of xr, which is 1.569. So we check if the product between the function of xl and fxr is less than, greater than, or equal to 0. So computing now, xl is 12 times xr, 1.569. So it's a positive value. So meaning it's greater than 0. So therefore, our limits now would lie between xr, which is 14, and xu equal to 16. So meaning for our next iteration, we repeat the process and we use now xr 14 as our new lower limit and xu as our, or xu equal to 16 as our upper limit. So for our new xl and xu 14, 16, compute for the functions of x, then we compute for the solve or compute for the root, approximate root, and xr now is equal to 15. The next step, compute for the function of xr and check if the function of xl times the function of xr, which is 1.569 times negative 0.425 is less than, greater than, or equal to 0. So positive times negative is negative, meaning it is less than 0. So therefore, the root lies between xl and xr. So for your next process, since it's less than 0 and not equal to 0, we repeat our process using now the new lower limit 14 and the new upper limit 15. So for our next computation, so we were able to solve already the functions of x, l, and xu of the new set. So we compute for the new approximate root, which is equal to 14.5. The function of xr now is equal to 0.5523. So check for the product of the function of xl and fxr. It's 1.569 times positive 0.5523. So it's greater than 0, meaning the root will lie between xr and xu. So again, repeat our process. So the new limit is 14.5, which was our xr a while ago. Xu is 15. So compute for xl and xu. Solve for the approximate root. So 14.5 plus 15 divided by 2 is 14.75. Solve for the function xr. That's equal to 0.0590. Check for the product of the lower limit and the approximate root. So it's 0.5523 and 0.0590, which is greater than 0. So meaning the root is between your xr and xu. So again, we repeat our process using now 14.75 and 15 as our new xl and xu. Then we compute for your xr, which is 14.875, the function of xr, which is negative 0.184, and check for the value of the product of fxl and fxr. So we have 0.0590 and negative 0.184, which is less than 0. Therefore, the limit is between, or the root is between xr 14.875 and xl equal to 14.75. So again, repeat the process using the new set of xl and xu, 14.75 and 14.875. So we compute for the xr, which is 14.8125. Function of xr is equal to negative 0.0629. So compute for the product of function of xl and function of xr, which is equal now to a negative value. Therefore, it's less than 0. So our root now is lying between xl and xr. So again, repeat the process. Compute for the roots or the approximate root using the new lower and upper limit. So we get XR equal to 14.781. FXR is equal to negative 0.002. So we check if the product again of function XL and function XR is less than, greater than, or equal to 0. And it's less than 0. So the root now will be again found between XL 14.75 and XR equal to 14.781. So again, repeat the process using the new set of XL and XR, XL and XU. So we solve for XR 14.766. Function is 0.0287. The product of FXL and FXR is greater than 0. So meaning the root is in between XR and XU, 14.766 and 14.781. Again, repeat the process using the new set of XL and XU, 14.766, 14.781. Solve for the roots. That's equal to 14.774. The function of the approximate root is 0.0131. Check for the product, the functions, lower and approximate root, which will give us a value greater than 0. So therefore, the root is between the upper limit 14.781 and approximate root 14.774. Repeat the process again until we arrive at value of XR, which will give a function of XR equal to 0, or we have a repeated value of XR. Okay. So new set of XL, solve for XR. So we get 14.778. Function of XR is 0.004. The product of the functions of XL and XR is greater than 0. So therefore, right, the root lies between 14.778 and 14.781. Okay, repeating the process, we have 14.78 as our XR. The function is 0.004. So for the product, approximately 0, since 0.004 times 0.004 is nearly equal to 0. So therefore, XR now is our true root of the equation for the drag coefficient. So therefore, the value of the coefficient is at 14.78. So that's it for the second method for open method under open methods for finding or determining the roots of non-linear equations. So thank you for listening.